In this video, I want to talk about functions as a rule. Now, I'm not going to go over basic functions. I think everyone's familiar with how they are. Practically, I'd like to review sort of the basics of a function, because that plays a role a couple times throughout the course. The function is essentially a rule that takes some input and assigns that input to a result. And it can be very general. The only characteristic of a function is that the result has to be unique. Or what I want to say is unambiguous. A function can't say, okay, given some input, well, it might be one of a few things. For a set of input, the result has to be unambiguous to be a good function. So, for example, in physics, we might see a function that looks like this. So, this is a length, and it is a function of t, which is a time, where this is some constant. In fact, this is a constant with units of meters per second squared, or let's say has dimension of length per time squared. And all this is really saying, if I write it sort of in our black box kind of way, we have a function here that takes some time as an input and outputs a length. And so, to use some other words from when we first learned about functions, the set of all possible inputs is called the domain, the set of all possible inputs, and the set of all possible outputs is the range. And so in this problem here, what is the domain? Well, I have a mathematical expression here, and I might say, well, I could put any real number t into that expression. But you know, in my physical problem, that may not be what I wanted. You know, I can imagine that this was some object whose I want to measure its position as a function of time, and I started the object as t is equal to 0. In physics, time only continues into the future, so there's no solution to this problem that I want where t is less than 0, and so I probably have in my conditions of my problem that I've limited my domain to well, t greater than 0, the domain for the real numbers greater than or equal to 0. And in that case, I might not really should have written my function that way. Perhaps the proper way to write the function, the rule, would be x of t is equal to two conditions, where it's 0 for all values of t less than 0, or 5t squared for t greater than equal to 0. This is the proper way to write that function where the domain is all real numbers, as any sort of mathematician would expect looking at an original function like that. So the reason I bring all this up is that this sort of thing is never done in physics. We simply give this expression. And so a lot of the math is implied in the context of the problem. Things like, well, time is never less than 0. And so you kind of have to be careful about that as you go through physics problems. We're using mathematics, and a lot of times we're skipping some of the mathematics steps that we might say is important if we look at it rigorously mathematically. What is the domain of the function, etc.? And we're using the context of the physical problem then to communicate that information. And so that's just something to look out for as we start to apply these mathematical concepts of functions to physical problems. Okay, so let me point out that let me just sort of there's lots of different types of functions that we might have, that we might see. You don't need single inputs. For example, you might have a function that inputs a length and a time, out of which you might get a force, for example. The other thing is that they may not just be numbers. One of the most important functions we'll talk about right away is the position function, which inputs a number. In this case, it's a time, and it outputs a vector, which in this case is a length or a position. So here's a function that assigns a vector output to number input. So the function concept can be quite general. So in fact, that can go the other way. We can have functions where you might end up inputting multiple vectors. In fact, we will. And the output is just another scalar. So we could input a vector force, for example, input a vector length, and the output might be just a simple number, energy. And you might guess this is not a coincidence. We will find functions that do exactly that. So vectors are a rule, but they can be very general in the types of input that they allow and the types of output that they give. So what we can say is that these rules do not have to be equations. A rule can be an equation. It can be a table, words, a verbal description of what happens, a graph. Doesn't have to be an equation. All it has to be is unambiguously assign the appropriate output given the appropriate input. So the final thing I want to talk about here is composite functions, which is simply putting two of these rules together. So let's say I have a rule, a function, which I call theta of t, which inputs a time and outputs an angle theta. And I have another rule, let's call this x of theta, that inputs an angle and outputs a length. I can put these two together for a composite function, x of theta of t. So if we want to see how that works, so I might have some function, theta of t, which is equal to 6t, input some time t, and it delivers an angle theta. And I might then again have some function x of theta, which we'll call that for sine theta, for sine of theta. Then I put these together for a composite function, and then x of theta of t is then just 4 sine 6t. So why is this important? Well, fundamentally, so we can chain the functions together one after another. Well, that that is sort of obvious. But also thinking about simply chaining them together, well, instead of just rewriting it here as a function of t, maybe I don't care about theta at all. The reason why it's important to think about this is noticing when a function is a composite function and can be broken up into two separate functions in this way is very important in doing a number of math, for example, the chain rule and other things we want to do in this course. So recognizing when and where composite functions play a role is also important.